All right, a little bit of review. These are common mistakes that kids made on that algebra pretest. So these are questions you saw already on that test, and these are common things kids messed up. How do you solve these? Well, you could just put both of them in the calculator and see where they cross. But you can't do that until you solve it for y. Okay? So there's a cool way that you could solve these called elimination, or you could do substitution, and I want to give you options here. If you solve this for y, and you graph them, they'll make two straight lines. You see where they cross, and that's the answer. That's a really slick way to do it. Calculators are allowed in the SAT and the ACT and most of our tests, so know how to do that. Next option, you could solve this for x by adding 2y to both sides. X equals 2y plus 3. Take that fact about x. And then wherever you see x, you could put in, right here, a little parenthesis, and drop in 2y plus 3. Then you got an equation, and you solve that little equation for y. All right, that's the basics of how you solve that kind. This one, so often kids think, oh, this squared plus this squared. Makes perfect sense, but it's perfectly wrong. What are you supposed to do on it? Yes, sir. X plus 5, yep. X plus 5 and x plus 5, and then you multiply it out. And what happens then? First, x squared. Outside, 5x. Inside, 5x. Last, 25. So if you just say x squared and 25, you're missing out on that part. So x squared plus 10x plus 25 right there. There's the right answer for that. Okay, that's a really common mistake. Next one. Why is this not right? It's really close to right. It's got the right y-intercept. Yes? It's a dotted line, and since this has an or equal to, it should be a solid line, and that would be that. All right, next one. What is the slope of a line parallel to this? Well, kids just go, oh, here's the slope, and so therefore I need a slope of 2. See how easy that is to make a mistake on? Why is that not the slope? That's not the slope. Yes? That's right. So really I have to solve this thing for y. That'll tell me what its slope is. So I solve it for y by adding 3 to both sides. X plus 3 equals 2y. Then I divide by 2. Divide by 2, divide by 2, divide by 2. And now I got y alone. And now it's x over 2. What the heck is that? X divided by 2. Same thing as 1/2. And the slope is 1/2. It should have been that. You get that? All right. I'm kind of fast here, but a lot of things to learn. Okay, next let's talk about the interpreting graphs. This is hits on a website. I have a website, and this is not my actual data. I just found this data because it was more interesting than my data. The hits on the website really depend on whether you're getting publicity or not. Can you see those 3 spikes? Those are probably has to do with publicity. Like, let's say that a website gets listed on Drudge Report. Have you ever heard of Drudge Report? He has a website where which got almost 1 billion views last month. So it's basically a news website where he takes the top stories that he thinks are interesting and he puts a link to them on his page. Okay, so he's got this page with a whole bunch of links, and it's links to other news organizations. So it's not even like he doesn't even do news. He just looks through the news for interesting stories that might not be making the front page, and he like puts links to it. So anyway, his page, and that's worth a lot of money when you have 1 billion page views. So anyway, his links to other people's websites get them a lot of business. So like if he puts something as a top link on his page, if there's 1 billion people coming this month, then a lot of people are going to click through to that and go to that person's website. So that could cause, like, let's say this is a website that has that he's put up a story that day, and this is like a website that sells news, and their news story gets a lot of hits because Drudge put it up there. Or maybe Oprah mentions your website. Boing! Get a huge bounce. If Oprah mentions a book on her Oprah's book club, it usually means that the person, whoever wrote the book, will sell so many copies that they'll be an instant millionaire. So isn't that amazing? Not only is she a millionaire, but she can, yeah, billionaire, sorry. She can make people a millionaire just by picking their book, and that'll make them an instant millionaire. She doesn't have to give them the money. She just has to say, this guy's book was really cool, and I think we should read this for our book club this week. And poof, they're a millionaire. Isn't that amazing? All right, moving on. This is the same data, except it's been smoothed out. Do you get, if you owned the website, that this wouldn't help you as much? Because it doesn't show you those big spikes, but they're figured into that. Okay, March is higher than it would have been because of that one spike that was in March, but you can't really tell there was even a spike. Okay, so sometimes the same data can be dumbed down by the way you graph it. All right, this one kind of has maybe the best of both worlds. It smooths out the data. The other one that showed the spikes was like really spiky all the time. It's hard to even pay attention to what the averages were. You can tell here it starts at about 2,000. By end of March, it's at about 5,000. By end of June, it's probably about 8,000. It's easier to read, and it still has the spikes. Right, so how you graph it can make a big difference in how readable it is for people. All right, let's talk about more stuff. This one is, it's important to look at the axes, and on the y-axis here, the number of people in the stadium. And on the x-axis, time since the game ended. Let me ask you an important question. Do you think the number of people in the stadium depends on how long it's been since the game ended? Or do you think the time depends on the number of people in the stadium? Yes. Yes. This depends on that. And that makes time not dependent, but what? Independent. And time is the ultimate independent thing. Have you heard this saying? Time stops for no man. Okay. And it's independent. It doesn't care what happens. It doesn't feel sadness. It doesn't stop for anything except Einstein theorized that it would stop if you ever went into a wormhole. He didn't call it a wormhole. Mr. Einstein worked out with Mr. Rosen a situation where they thought could be a bridge between places where you could travel there instantaneously. If you went into this one spot, that it would overlap with another spot in space that could be billions of miles away, and you could transport there instantaneously in 0 time. Now, these are really smart guys. They weren't just like making up a science fiction story because they wanted to, like, you know, have a cool TV show. They actually thought this was possible. So maybe there are wormholes, and maybe that could explain some things about how, you know, how everything goes together. We still haven't got it all figured out yet. There are some pretty amazing things out there with black holes being, you know, where the reason it's black is that it's so much gravity that light can't even escape. It pulls light back in. And all right, so what is the real world meaning of the graph? Well, it just is talking about how many people are in the stadium since the game ended. So here there's a lot of people in the stadium. Here everybody's gone, so that's 0. Okay, and it's time from here to here. Do you think in the real world that it goes like that after the game? It does decrease, and eventually it's 0. I'll agree there's a lot of people in the beginning, and there's no people there at the end, but do you think it's seriously a straight line? If you were to graph it? Probably not. Because then what would that mean about the people leaving? Same exact number of people. Every second, like a certain number of people would have to leave. Like, say, 4 people every 1 second or whatever. And they'd have to not leave it faster at the beginning and slower at the end. They'd have to be leaving at the exact perfect rate all the time. And that just doesn't happen in the real world. And there's other things about people and how they move that make you think that this wouldn't be this way. People tend to like be in packs. So I want you right now to graph for me. Don't have to label it, just make an X and a Y axis, and I want you to say Start at the same spot, start high. There's a lot of people in the stadium at the end of the game. And then tell me how you think it will go. Do you think it'll go like this? Do you think it'll go like this? Do you think it'll go like that for some reason? Just give me a quick graph of what you think the real world number of people left in the stadium graph should look like. Right now, on paper. Now this is the part where if you don't have an iPad yet, which I know you don't, then you need to be doing this on some spiral notebook paper or 3-ring notebook paper. Very soon, very soon, you'll be using iPads. Although I doubt you'll have them by the time you get here tomorrow. So it'll probably be Wednesday, first day we'll use them. I thought I heard it was going to be science, but I do not. You actually get them in English, but then you'll learn about how to use them during science. Gotcha. You have to, I understand. At the beginning, we're going to be pretty generous with letting you ease into it, because in the first couple of days, you get to be so clunky that it'll be hard to take good notes and whatever. But, I know. Don't worry. We'll ease you into it. You won't have to know it all. All right. So, what did you see? Well, one of the cool things, if you had an iPad right now, is I could say, "Hey, Jake, send this to me," and it would take you 2 seconds. You just take a picture of it, and then you tap the picture, and then you say email. There's one of the little links on the, once you tap it, pulls up these little options, and you say email, and you email it to me, and I could go to my email, and then like literally in about 8 seconds, you can have sent it to me, and I can open it on the screen. So it's kind of cool to see exactly what you really drew. So, and I can put like 4 or 5 people up here really quickly to see different ways what people thought. So, all right, I am just going to show you. There's a lot of, here's a typical deal. A lot of people say that it goes down fairly fast and then it mellows out, like more like that. Raise your hand if you kind of went that way. Okay? And then there's another one where people say, and that's assuming, by the way, that it goes really fast at the beginning and then really slower later. Notice the slope of it is what I'm talking about. If I say really fast, it's really steep. And that means it's changing a lot. In a short period of time, from here to here in time, it's going down a lot from here to here. All right, so steeper at the beginning means you think a lot of people leave right at the beginning. But what if you had a little lag here and then you had a bunch of people leave? What's the logic there? Why would you do that? Yes? Takes time to get from the stands over to the door, yes. If this was time before you get out of your seat, a lot of people, right when the game ends, they stand up, right? But that doesn't mean they all walk out the door instantly. So yeah, good point. All right, so you might have a little lag at the beginning, and then it might go kind of fast, and then why might it like mellow out like that at the end? Yes. Yeah, some people just want to hang out. Maybe it's like, if nothing else, coaches, I don't know, some parents will stay there and chat with other parents after the game. Some people wait in the stadium for their kid to be done, so with getting their stuff or whatever. All right, moving on. Independent versus dependent. I already talked about this, but I'm going to say the ultimate independent thing is time, and independent things always go on the bottom, and the ultimate dependent thing is money. I'll give you an example. How much does a glass of water cost, or a bottle of water cost? I've heard $0 if you get it out of the tap, all the way to $2.50 is pretty typical. Like, and have you ever seen it like $3 or $4 for water? Yeah, isn't that crazy? The thought of paying $4 for something that is free. I mean, you can get free. Now, in some countries, you just can't get it free. Like, it's really hard to get water in some places. Even in some places in the United States, it's getting tougher and tougher to get clean water. Um, in fact, did you know there was a proposal to take the water from uh, Lake Superior and run a pipeline of fresh water down into Arizona? Yep. They were actually like, really contemplating if they should do that because we've got all that fresh water there. It is true. There is so much fresh water in Lake Superior. And run it down to Arizona where I don't have any. So there would be some bad things for Lake Superior. You'd probably lower the level of Lake Superior, but let's say if they only promised to lower it by like 2 feet. And they could, if you just take 2 feet off of Lake Superior, it's a lot of water. All right, so anyway, how much is water worth? Well, it depends. If you're a really rich guy and you're really thirsty and the restaurant was selling it for 20 bucks, and you were like really thirsty, like you're just parched, you think you're gonna get sick, do you think you might pay 20 bucks for it? No, I'm surprised if there aren't more stories about people that are willing to pay almost anything if they get really, really sick, or prices, things can go up dramatically depending on how much you need it. If you really don't need the water, you're not going to spend 20 bucks. You're not going to spend 4 bucks. You're going to laugh at them. But then if you're like, you have a cut on your hand and you got to get it washed out, otherwise it's going to get infected or whatever, and then you buy the $4 water. Yeah, I guess whatever. I need it. So it depends on how much you need it. All right. So depends. Money depends. Cost of things. It's so variable. So dependent. But time doesn't stop for anybody. So it's a very independent. So if I was going to ask you between these two, time versus temperature, well, it's an automatic because at times one of the ones that's guaranteed. Which one's independent? Time. I know some of you think temperature is independent because it's also something like time that doesn't seem like it's affected by anything, but sun comes out, doesn't temperature go up? Yep. And if there's snow cover on the ground, doesn't temperature go down? Yep. Even the same amount of sun shining down, if there's this constant like layer of snow, the sun can't like heat up the ground near as much, so it can't get as warm out outside. So time is independent, temperature is not. Temperature depends on other things. But what if you were picking between ice cream sales versus temperature? You're going to graph those two. Which of those two is more independent, and which one depends on the other one? What do you think, Z? You think temperature's independent, and then that means you're saying that ice cream is dependent. Explain why. Mm-hmm. All right. So you can't look at the ice cream and say, I know, even if it's cold, I still like ice cream. But you got to admit, if it's a really hot day, you can expect the ice cream stand probably sell more than if it's a really cold day. Because if nothing else, there's less people around because it's cold inside. Okay, so ice cream sales versus temperature. Ice cream sales depend on the temperature, but the temperature doesn't depend on the ice cream. Think about how ludicrous that would be. They sold lots of ice cream. Look, the temperature's going up. Doesn't make sense. Okay, cost of food versus location. Which one's independent? Yes. Yes, and the other way you could know that is because I said cost or money is the ultimate dependent. So cost and money, they have to be dependent. So the cost of food depends on the location. And that makes sense, right? If you're at the state fair, it's going to cost more for your hot dog than if you're at SA. You can get two for $1 at SA, and it's like, one hot dog for $3 at the fair. Yes. There can be, but it's very rare. I can't give you even one off the top of my head, but I know the only thing I would never limit is I wouldn't ever want to say that time depended on something else. Time is always independent, but money, I can picture a scenario where you could find something else that was dependent on the money. Like how much you sell would depend on the price you sell. Right? So I guess that is easy. So would your income depend on your house size? The house size would depend on your income. There you go. So it's really, you're right. You've got the point where the dependent one is is the house size, and your income, which is money, is the independent. So yeah, yes. Yep, where the bottom was, but the bottom would be shares instead of money, which is close, but it's not the same, but it's close. All right, this one, increasing versus decreasing. This is really obvious because we always read from left to right, so I bet automatically you'll know this one. What's this? Increasing. Okay, because it's from left to right. What's this one? Decreasing. What's that one? Parabola is not the answer. Parabola is what it is. Is it increasing or decreasing? Yeah, you see these arrows that go up? Doesn't it seem like it's just increasing? But it's not. Remember, we read from left to right, so it's both. What's this part? Decreasing, and then this part? All right, that can happen. It could be like, how warm is it outside? Well, it starts out warm, then it goes down overnight, and then it goes back up again in the morning. So it can be decreasing and then increasing. How about this guy right here? Decreasing. And it's different than all the others. It's decreasing at a constant rate. Exactly. So that brings up the topic of, if this is increasing and this is decreasing, and this is increasing, but it's increasing at different rates at different times, do you get how at the beginning it's increasing very slowly? And then in this little zone it's increasing very quickly? Okay, so this is increasing at different rates, but it's increasing the whole time. Now you have to start to say both things. Is this generally increasing or generally decreasing? This is generally decreasing, but is it decreasing at a constant rate? No. So we could say that this is decreasing at an increasing rate. Let's talk about it again. Do you get that it's decreasing? Now, let's talk about the rate at which it is decreasing. Do you get at the beginning that it is that it is decreasing, not super fast? It's kind of decreasing kind of slowly, because the slope of that line right there is not real steep. But then do you get how right in here it's like decreasing really fast because the slope there is really steep? So it's getting faster and faster. So that's exactly. So it's decreasing at an increasing rate. How about this one right here? Is it generally increasing or decreasing? Increasing. At what kind of rate? At an increasing rate, because it starts out slow, ends up fast. So that's increasing at an increasing rate. So I want you to right now try to sketch me decreasing at a decreasing rate. Decreasing at a decreasing rate. Just make a little XY and then just draw me a little curve and try to figure out if it's decreasing at a decreasing rate. And what you do is try it and you go, okay, let's see. Decreasing, let's say I did that. Is that decreasing at a decreasing rate? Huh, I got it right off the bat. Why? Because it was going really fast, and then at the end it's going kind of slow, so it must have been decreasing. That's decreasing at a decreasing rate. What would this one have been? Decreasing at an increasing, because it starts out kind of slow, ends up really fast. All right, good. So I think we talked about all of those. What is this part of the graph right here? And don't say increasing or decreasing. Yes? Yes, there's a word for stay the same. Constant. So this is increasing at a constant rate. This is just plain constant. Think about your oven. You turn your oven on, you set it for 300 degrees because you're going to bake something. Okay? So the oven gets hotter and hotter and hotter until it hits what? 300, and then what does it do? It stays constant at 300. It keeps heating it just enough to keep it constant. Now, technically, your temperature in there is going down, and then it goes down enough and it kicks in some heat, and then it raises it back up, but it kind of holds it like this. They try to keep that very tight so that it's really not decreasing much, but it's gonna, if you really graphed it closely, your oven would have to be going down a little bit and then to heat it back up again. But you could kind of generally sum it up to say that it's just constant. So it's staying the same. This one's increasing at a constant rate. All right, so that's the new thing for today. And the domain and range is just this. The domain is the X stuff. Range is the Y stuff. So if I were you, I'd write that down. Domain X, range Y. Because you're going to forget. And it's stuff that's on the test. You want to know. Eventually you'll be tested on this stuff. It'll take you at least a week before we're ready for any kind of test. All right. Let's look at this pop machine graph for our last thing. Do you get how the number of cans in the machine starts at full, and then all of a sudden at 8 a.m. it starts going down? Why would it start going down? We start buying pop, okay? And then what happened right there? Filled it back up. That's the only way a pop machine can go up, right? And then after it's full again, all of a sudden it's not like nobody touches it for a little while. I don't know, maybe I don't know. Maybe your kids are all in class or something because this is at school. And then all of a sudden at noontime it goes all the way down to 0. What happened? Yeah, lunchtime. Bought it all out. Okay. Then they bounce back up again here because that's filling it back up. Maybe they didn't have enough cans to fill it all the way. I don't know. You can make up a lot of reasons for these things. All of a sudden it's almost empty again at 3. What's that? After school. And then all of a sudden they fill it up again and then it still goes down. Why? Teachers, maybe kids in sports. Seconds. All right. Good enough. And I don't want to do any more of that. I think we've learned enough for today. So, just want me to pop them. It's got this new thing that. There we go. Juicy juice. Anyway, they got this new thing that it's not quite working correctly. All right, that's it for today.